Now, don't memorize this, but you do need to be familiar with it because we modify this to break stuff and steal things, or other people modify it to break stuff and steal things, and we have to stop them. But we also use this all the time to do our business. So first thing we have to do is we have to say, all right, well, I have this, but chances are that other computer didn't want to just talk to TCP. I mean, maybe it did. Maybe there's a windowing problem or something. But we need to be able to communicate with the layer 4 protocols. And layer 4 protocols are identified by port number. So we have the source port number and we have the destination port number. And that is 16 bits for each one. So 16,700 and something or other port numbers that we can have. We also have sequence numbers. And the sequence numbers are from the receiving machines, or from the sending machine, that tells you your sequence number. And they also may do an acknowledgement number that says, I acknowledge this is the one that I'm expecting next, the next segment. These two numbers are not going to be even necessarily even close to each other. Because when we do the TCP three-way handshake, we do the request to synchronize, and then acknowledge and request to synchronize. I tell you my sequence number here, you tell me your sequence number here, and you in fact acknowledge mine, and then I acknowledge yours, and then boom, we're back in business. So my sequence number may be 7, and your sequence number may be 14,216. So they can be wildly different. It also tells us how big the header is. We have some reserved stuff, some code bits. These codes is where we will have one of the bits that is labeled as the SYN flag, S-Y-N flag. And that tells me that it's a request to synchronize packet. We also have one that's called the established flag. The established flag says that I'm responding to communications that you'd already sent. So normally with a firewall in our company, so here we have the internet, we have a firewall, and then we have our machine. And if a packet comes in and it says, oh yeah, I'm for port 2197, and I don't have that established bit set, that's telling me you're trying to initiate communications to port 2197, and you don't already have a socket established. Remember, a socket is a port number and an IP address for both the source and the destination. That establishes both sides. And since I don't have the established in there, I would have to have a proxy server that allows you to come in via port 2197, or I would have to program my firewall to let that through, but I'm not going to do that. Most of the time, firewalls will block just about everything, unless I say, hey, I'd like to communicate with you. I'm using port 2197, and maybe I'm going to your port 443. And then when you come back, you say it's established, but it's from port 443, and it's to port 2197. The firewall will see the established. It'll let it through. It gets up to this machine. The machine sees it and says, hey, do we already have a socket set up? Oh, it says it's established. Yep, we have a socket, and then it knows which transmission path to give it to. So here's our window size that we can tell. We have a checksum to make sure that all this stuff hasn't got corrupted. We can have an urgent pointer that tells us where our data that is urgent, jump right to it goes. But this is just regular old TCP. The big thing that we need to know of is source port, destination port, sequence, and acknowledgement numbers. That's what I would memorize. I wouldn't memorize where they are or how long they are. Just know that they're in TCP. Also know that TCP is connection oriented, which means we have to do acknowledge. It's like sending registered mail all the time. That's what we have. If you get into CCNA, yeah, you're going to have a lot more that you have to remember. Now, see how big and fat this is? Plus, we have to do all these acknowledgments. This is TCP. Let's look at UDP. The only thing the UDP has is a source destination port number, a length, and a checksum. That's it. There's no window, there's no acknowledgement, there's no sequence number. That's because this is considered, well, it's not considered, it is an unreliable protocol. Unreliable? Does that mean it's bad and borrows money and doesn't pay it back? No, it just means that it doesn't do reliability as part of the protocol. If you can have reliable communications using UDP, it's just that the application that uses UDP has to take care of it for you. So, for example, we use trivial file transport protocol to transmit configurations from Cisco to a TFTP server. It's unreliable, but boy oh boy would I want to make sure that my stuff gets there. So the TFTP client software that runs on the Cisco router and the TFTP server, they make sure that the file gets there. It's handled at a different layer of the OSI stack. And that's the only difference between a reliable protocol and unreliable. A reliable protocol has pieces in it like sequence numbers and acknowledgement numbers, has pieces in it that allows me to say whether or not it got there properly. Unreliable protocol, hey, you have to do the reliability somewhere else because we're not going to do it right here. So it's really, 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 really nice and fast. Here are the key concepts between TCP and UDP. One is sequence, one is not. One is reliable, one is not. One is connection oriented, one is not. One does a virtual circuit, one does not. There is a bunch of overhead, there is no overhead. We do acknowledgements, we don't do acknowledgements. We have flow control, and windowing, we don't have it. Memorize this. You may see this again, and it's also just good to know. The big thing to remember, we don't have sequence numbers, we don't have acknowledgement numbers, it's not reliable, so anything associated with reliable, like virtual circuit and windowing and flow, no, it's a postcard. I write down my data, I throw it over the wall, and then I never think of it again. I don't have an established connection, I just send it out the door and away you go. All right, so now, port numbers. Port numbers simply tell us what upper layer protocol we hand it to. And that's why we had you memorize all of the port numbers. And the good news is, over on page 192, we have table 6.2. These are the ones you want to memorize. And one that is in particular oddity and importance is DNS, because it uses the same port number for both TCP and UDP. So do yourself a large memorize this chart. I get emails come back from students. I memorized the stuff you told me to memorize and I passed the exam. So yeah, you do have to memorize it. All right, now let's go ahead and look at some helper protocols that work along with the internet protocol, the IP protocol, and this is just the generic one. So first thing, let's go ahead and look at layer 3. Let's peel back the IP header. This is the IP header, and just like on all the other headers that we looked at, don't bother memorizing it, but let's go ahead and see what we have in here. The first thing that we want to look at is we want to look at our time to live. We have a TTL. And the reason that we put TTLs on IP protocols is because sometimes routers get misconfigured. For example, we have these two routers are connected to each other, and we'll say that this one's IP address is 10.1.1.1, and this one's IP address is 10.1.1.2. And I will tell this router that this one is its gateway, and I will tell this one that this one is this gateway. And so then I send a packet to 5.9.7.3 or any other address. It doesn't have to be in the 10.1 network. And because these are pointing to each other as their own default gateway, this packet will just bounce back and forth and back and forth and back and forth and back and forth. And if we did not have a time to live, it would do this forever. But because we have a time to live, this time to live value is decremented every 30 seconds of a second, and it's also decremented every time we pass through a router. So if my time to live, we'll say, is 50, it would bounce back and forth here 50 times, plus minus 30 seconds of a second, until it gets to 0, and then whoever has it last, it's like hot potato, they would send an ICMP command that says, oh, by the way, your packet timed out. Destination network unreachable or something like that, or packet timeout. So that's why we have a time to live. And that's why you have to be very, very careful at layer 2, because layer 2 doesn't have a time to live. And if we have a packet that somehow gets into a routing loop, it will never stop until you start unplugging cables. So yeah, very, very, very important. We also tell you what protocol. This is what upper layer protocol, TCP, UDP, Doug protocol, whatever I have here. And here is the header checksum. That is because when the packet finally gets to IP, it doesn't check the entire data frame. It's not going to like do a frame check sequence. We do that at layer 2. But here what we do is we just check to make sure that the header is not messed up. The other parts beside the time to live, there's really only 2. You have the source IP address is where it's coming from, and you have the destination IP address of where it is going through. And there could be other other commands and switches and things. But the big thing to remember, time to live, source IP address, and destination IP address, and mostly source and destination IP address. That's what we are going to want to pay a lot of attention to. Now, I said that as we were bouncing these packets back and forth, eventually the TTL expires and then the router tells us. That's because at the IP layer, layer 3, we do have ICMP. ICMP allows me to send messages back and forth. So if I do ping to somebody, I say, hey, ping, this is a packet internetwork groper. That's what ping stands for, packet internetwork groper. It uses ICMP. And so what I will do is I will say, hey, I want to ping you, and then if this supports ping, if it supports ICMP, it will go ahead and ping back. The problem with ping and ICMP is that I can use it for reconnaissance. Remember when I talked about war dialing, where you had the range of phone numbers, start at the top, go to the bottom, dial each one. Anytime that somebody answers, you put it into a database. We did that with phone lines. But I could also do it with a war dialer for IP. They have the Angry Zyber war dialer, which is really cool. And what it does, you put in a range of IP addresses, and it will ping all those IP addresses and write down everybody who answers. So what a lot of folks will do is on their firewalls, they will block ICMP because I don't want you to be able to get through it. So for a very long time, if you tried to ping www.microsoft.com, you would get no response. And so you'd be, oh no, the internet's down. And yet if you ping google.com, it worked. But since then, Microsoft will allow you to ping them sometimes, usually. And you can use that to find out. Now, also, let's say that I have a bad routing table. And the routing table says, let's say I had a connection here to the 1.5 network, we'll pretend. And so it was shared here, so this one knows to get to the 1.5 network, we put it right over there. However, the network went down, and I just haven't heard about it yet. And so I want to send a packet to 1.5, I send it to the router. The router looks at the routing table, do I know how to get to 1.5? Oh yeah, I send it over here. When I send it over here, this router says, hey, wait a minute, I no longer have a way to get to 1.5 because I was the only one that I knew how to get there, and I can't get there anymore. So what it may do, all of these ICMP responses are entirely optional. No device in the entire universe is mandatorily required by ICMP to give you any message whatsoever. And I can turn them off, and I can also filter them. What a lot of people do is they'll just put a firewall that just filters all of them, and I don't have to bother turning it off on the individual machines. But if this machine is nice, it will go back and it'll say destination network unreachable. And that tells you it's not just an individual host that I can't find the entire network. And it helps us out. Now there's some other commands that we may have. These are over on page bottom of page 194 and top of page 195. Destination unreachable means I have no idea how to get to the next step. There's no way to get there. If it says buffer full, it means that you're sending me too much data. And so I'm just telling you, by the way, you're sending me too much data. If you send me more, I'm just going to discard it. So I'll just send you a buffer full. Hops will tell me how many hops we're going through stuff. So I can say, hey, only go through so many hops. And in fact, there's a ping command that we use with a expired TTL. It's called traceroute. And let's say that I wanted to find, I'm having a problem getting to this network, and I want to find everybody that's all along that way. I can use traceroute. And what I do is I send a packet with a TTL of 1. And then it goes to here, and this one, it'll expire it, and then it comes back, and I will get that IP address. Then I send it with a TTL of 2. It goes over here, this expires it, and it replies back, and now I have that IP address, and then so on, and then so on, and then so on. So what we're doing is we're modifying the way ICMP is supposed to be working by sending out expired packets. So we have that. And that's what traceroute does. ARP, we already know about. The purpose of ARP is I do broadcasts. Hey, what is your MAC address, IP address 10.1.1.2? And I broadcast that out to the MAC address of 6Fs. But I do have the IP address of the actual IP address. Then that goes on layer 1, and everybody in my broadcast domain will absorb that in layer 1, hands it up to layer 2. Layer 2 says, is this for my MAC address? Or is this for a broadcast, or is it something I can discard? Well, everybody says, oh, it is a broadcast MAC address. So it absorbs it in layer 2, and then layer 2 says, oh, it's an ARP request looking for this IP address. Let me talk to layer 3 real quick. Hey, what's our IP address? Oh, it's not that. We throw it away, except for the one machine that does have that IP address, and then it replies back, and I can find out what your MAC address is. That's what we can use. So here is a ARP broadcast. This is a packet sniff. It's kind of in a weird format, but this is the same thing that we have over on page 196 and 197. Notice that we have the destination of all ones. Here is the source MAC address that we have here. We identify the layer 3 protocol, which is going to be ARP. And then away we send it out. And we tell you my address and the sender's address. The target address we're going to ignore, even though the destination is all ones. And the IP address we're looking for is 172.16.10.10. And then you'll also see in a lot of those headers, they had padding. That's because they want it to be a nice square box. It's easier for the computers to send, because I know that it ends at a certain bit length. And so all that they do is, if the data doesn't quite match exactly on that certain ending point, they just put padding in here. And so don't worry about the padding, it just makes it good. And then we'll also compare all this and do a frame check sequence to verify that when I absorb it, it hasn't been modified. But we've pretty much seen this before. Reverse ARP is if I know my MAC address, but I don't know my IP address. This was sort of a precursor to BootP protocol, where I would have machines that say, help, I need an IP address, and it sort of kind of does it a real similar way as this goes. Another important concept, and I've been dancing around this one for quite a while, encapsulation. What encapsulation does is I have different layers, and it could be layers in the OSI model, it could be other protocols, it could be encryption, it could be where I'm going to encapsulate one protocol into another, like IPv6 inside of IPv4, IPv4 inside of IPv6, or IPv4 inside of IPX, SPX. So all you're doing is you're taking the data, and this data is a different protocol, and I encapsulate it in another protocol, and then I send it to the receiving machine who has both protocols. It peels off that first wrapper and says, what am I supposed to do with this? Oh, I'm supposed to hand this up to layer 3, then it hands it up to layer 3, and then layer 3 can handle this however it needs to handle it. So all that encapsulation is wrapping data, for some reason, wrapping data and then putting messages on that wrapper so that when it gets to the other side, they can unwrap it. And we see this all the time with TCP because we go through a variety of protocol data units. We have segments, packets, frames, and bits. The data from the upper layers becomes the data for the lower layers. They add headers to it. All of that becomes the data. Now it's a segment. We add headers to it. Now it becomes a packet. We add an LLC header, and we'll add a MAC header to it. And then all the way down here it becomes bits, and we send it across. You have to know the protocol data units. And the way that I remember it is salty peanuts for beer. Segments, packets, frames, and bits. This is layer 1, this is layer 2, this is layer 3, and this is layer 4. So they encapsulate it on the transmission side, and then on the receiving side, they decapsulate it. Layer 1, layer 1 has no intelligence, it just sucks it up. Hands it to layer 2. Layer 2 says, check the frame check sequence. Is it from my MAC address? Oh, it is. Let me peel it open. Oh, we have another protocol in here. Oh, look, it's IP version 4. It even has the protocol label. So IP version 4, here you go. IP version 4 takes it, peels off the encapsulation for IP version 4, and says, what the heck is this? Oh, it's TCP port 80. Okay, so then I hand it to TCP port 80. TCP port 80 takes it and says, what the heck is this? Oh, look, it's MAPI embedded inside of HTTPS, and so what we need to do is we hand it over to the Exchange server. So you can encapsulate stuff and other things. And that's one of the things that hackers will do. If you do not allow, for example, you don't allow remote desktop protocol, no port 3389. I've been with companies that did that. No port 3389. So all that I do is I have a gateway that takes port 3389 packets encapsulates them in port 80, goes to another machine that decapsulates it from port 80 and then turns it back into port 3389, and guess what? I bypassed your stuff. And that's just simply called double encapsulation or re-encapsulation. And it happens all the time. I mean, all the data that I have when I'm transmitting a Word document, the Word document is the data that's encapsulated with this, it's encapsulated with SMB, that's encapsulated with TCP, encapsulated with IP, encapsulated with MAC address stuff and frames, encapsulated down here, and then it just gets peeled off as it goes.